Hey guys, how's it going? It's ready to go. Just close a few windows here on my laptop. Maybe before we start, I'll make another disclaimer about rows and columns so that there's no confusion about this when you work on the assignment, for example. It's coming up. So I'm just gonna make this a big warning. How do I phrase this? Well, I could say that everything we do with with columns. For determinants, is also true for rows. So as just an example, so we had this property of multilinearity. So we had it's multilinear. So this means that for this can either be viewed in terms of columns. That's what we did in this lecture. And then we said that the determinant of two columns x plus z comma y is equal to the determinant of x comma y plus the determinant of z comma y. But we could have also done the same thing for rows. And then we would have said that the determinant of this is the reason why I don't like this notation, but of x plus z as like as columns. So just imagine you have A, B, C, D, and then you have A plus U, B plus V. So then this is the sum of two rows. Or two row vectors, I should say. So that you can think of this as the one row vector AB and another row vector UV, AB and UV. So this would be equal to determinant of AB CD plus the determinant of UVCD, where these two vectors are written as rows. So we have the green and the yellow, and then we add these two rows together. And before, so here on the left-hand side, we would have determinant. So this is the cut between these two viewpoints, rows and columns. On the left-hand side, we have the determinant of A, B, C, D. But we add a column we had another column. So this means we had to have AC, and we would have UV. So this is the sum of two columns, both together in the first column of this 2x2 matrix. And then we can write this as the determinant of A, B, C, D. And now I have to do some shrinking magic. Plus the determinant of UV BD. So the right column never changes. And in this example, the lower row never changes. It's just that we can separate a row into two sums, two summons of rows. Then we can separate the determinant into two determinants, where we take into account each row once. So this row, this column are rows taken first, and this other one in a second. Any questions about what multilinear means or about this? Just so that there's no confusion of that columns and rows are interchangeable. I just find columns much nicer to work with in terms of notation. Yes, Andrew's question is correct. Multilinear means just linear in both arguments, or if we have more than two arguments, which we're going to do right now. So we're going to continue with what we had yesterday for 2x2 matrices, and really continue and do the same thing for n by n matrices. And then we don't have just two arguments, but we have n arguments. And then I need to replace the phrase linear in both arguments with the phrase linear in all arguments. And that's just what multilinear means. Okay, so remember that yesterday we left off with this remark that there are three nice properties: linear in all arguments, two or more; alternating, so if you did change two, then it's minus the expression; and the determinant of the identity matrix is 1. So now let's look at the next page. So when we have a function, and let's just call this f. So f is a function that makes sense to evaluate on n vectors. So we say that, let's just call this f. So f takes inputs, f of x1, x2, x3, and so on. And we can actually write this f just in terms of giving it a matrix, and then we just think of the x as the columns. So we could write this as f of a matrix, f of A, where A x1, x2, and so on, all the way to xn, has columns x1 to xn. So that's just notation which might be more convenient in one or the other case. All right, so what does it mean to be multilinear? As Andrew's question already suggested, or as my answers to that suggested, if we have x1, x2, at any point we have xi plus z. So in any of these, this could be the first, the second, the last, doesn't matter. If any of these arguments is actually sum of two vectors, then we want this to be the function applied to all the vectors x1 to xn with the first summand. And then we add to this x1, and this time we take z. But this is still the same position. So this is still the ith position in the arguments. And also, of course, this is just a sum, but we have two operations. We also have scalar multiplication. So if you have f of x1, x2, and so on, and you multiply xi with a constant c, then we want this to be c times the function evaluated on the vectors, on the n vectors. So this is what multilinear means in general if you have more than two arguments. Alternating is very similar too. So you can guess what it means. If you have a function that evaluates on n vectors, so this is this is what we can call it. So it's x1. It has somewhere an xi on the ith position, an xj on the jth position. So I'm just saying that I and j are just some indices. Then what we want is that if we did change these two, this should be minus the same. So we have the xj on the ith position and then the xi on the jth position, and nothing else changes. So only these two get swapped. Then I want there to be a minus sign in front of the function. And we saw that this is true for the 2x2 determinant. This is just making it more general. And of course, normalized now means that f of the identity matrix of size n by n, which we can also think of just plugging in the standard vectors. Remember that ei is the one vector with just one non-zero entry. So e1, e2, en, this should be equal to 1. And we saw that in terms of the 2x2 matrix as well. So our goal for today, for the first hour, is to make sense of, to find a function that satisfies all these properties on our wish list. The last f on the first line should only have zeros in z. No. It has the same axis. So if you compare, so that was Zach's question in the chat. Compare this expression with what I wrote here. So when you have an x plus z in the 2x2 case, then you first do everything like the y is unchanged for the x, and the y is unchanged for the z. You just split it up. So it's similar for saying that we had t of x plus y. Let me do x plus z. It's equal to t of x plus t of z. That was what means linear. This is part of being linear for a transformation. And now we just fix everything but this one argument, and we say it has to be linear. In this argument, everything else is unchanged. So you can think of t as taking the determinant where the argument goes into the first argument, and then the second one is fixed. Does that make sense? Okay. Forgot to turn the light on. Maybe this is a bit better. All right. So now that we know what we want, now we have to hope that it actually exists. And in order to tell you that it exists, I need to tell you first just some notation. It's called the ij minor. So if you have a matrix, and this is just very general, let's just call this this A with entries A11, A12, A13, all the way to A. This is some AI. No, sorry, there's some A1J, A1J plus 1, A1N. And then we go down A21, A31. At some point, there's an AI1, and so on. And then there's an AN1, and then this is an N. So you get the idea. This is just the usual indices that we give. Then if we strike out the ith row and the jth column, if you just forget them, if you just literally just cut out left and right from this column and this row, and then you stitch it back together, we get a new matrix, but it's missing one column and one row. And we call this the ij minor if we did this surgery operation at the ith row in the jth column. So I'm just gonna just delete this row. There would have been A2j, A3j, and so on, and A nj. So all of them are going to be gone. And same for the ith row. I'm just going to delete all of them. So the resulting matrix will be of size n-1 times n-1. And you could write this. So the aij is supposed to be that removed. And then so if you start with a11, then you have a1. I was going to try writing a j minus 1. There's no aij, and you continue with a1 j plus 1. So this is what the a1j used to be, but this is gone now. Likewise, the ai minus 1 1 is followed directly by the I plus 1 1. Maybe this is not really illuminating. Let's just look at this discussion, and then I think this should help much more than any kind of abstract notation. So please just take a minute, and this is really not hard if you understand what I was just trying to say. What is the 823 minor of this matrix A that I've given you? So Andrew says this should be 1, 2, 7, 8, and Jagat agrees. So how do we compute this? Well, I told you, you just need to find the second row, which is this, and strike it out. So just forget about this. And the third column, which is this, just forget about this. And then you just read off what's left over. And this is exactly 1, 2, 7, and 8. And then you just stitch them back together. If there was more stuff on the right, you would stitch it back here, and you would just forget this column. Any questions about this? So we're going to use this, and this is not the last time that you'll see the minor. Just if there are questions, then this will be a good place to elaborate. Okay, so with this notation in mind, let us look at the proposition 325 from the book. And as I said, the book has a different approach to determinants. It's longer, and it's somewhat more abstract and more mathematical precise. It's more elegant, maybe. What we're doing is not imprecise. So the book says that among all the functions that we can apply to 3 vectors, there's only one single function that satisfies all the things on our wish list. And that was, remember, it was multilinear, so that we can like separate them out if there's a sum of 2 columns. It's alternating, and the fact that f at in at the identity matrix evaluates to 1. So those are the 3 things that we had on our wish list: 1, 2, and 3. And it turns out there's only one such function. And this is again what the book calls the determinant. Well, the reason that this is very abstract is because it doesn't tell us what it is. It just tells us it exists and it's unique. But it's not very practical in terms of computing anything, because we don't know what it is yet. So we need to find what it actually looks like. Now, the definition of a 3x3 matrix, for a 3x3 matrix, the determinant can be defined to be depending on the minors of the 3x3 matrix. So what the definition in the book says, and we look at this first, is if you have a 3x3 matrix, so it's going to look like A11, A12, let me just do like dots for the entries. Then in order to compute the determinant, you need to compute minors, namely this is the minor A11. If you do this again, then this minor would be A12, so you would strike out this. And so it says that the determinant is the sum of determinants of minors. So why does this help us? Well, this is a recursive definition. It uses the 2x2 matrix, which we already know, determinant of A, B, C, D which is AD minus BC. And it says, well, if you have a 3 by 3 matrix, then you just sum up 3 different 2 by 2 matrix determinants with coefficients. And then you get the determinant of the 3 by 3 matrix. So the A11 is the entry, actually. This is the entry of the notation is that A11 is the first entry of A, and then we have A12 right next to it. Below it is A21, A31, A22, A33, A23, and A32. So as you can see, what this is using, these coefficients are exactly the entries of the first row of A, and then the way that and then we multiply this with the determinant of a minor, which is exactly the one that we get by striking out the first row and the column in which this entry was. Okay, long story short, let us just compute an example, and then we'll see. Then we'll probably understand this better. So I'll give you 2 minutes to compute the determinant with this definition of this matrix shown below. We'll not implement a recursion. This is going to be, we just use it for computations. So the question isn't what the answer is, because I actually didn't know the answer. I just had to do it myself. The more important question is, how do we get there? That's the purpose of this discussion. So can someone tell me what do I write down if I wanted to compute the determinant of A? Someone please tell me what to write. And you can just raise your hand and then say it out loud. Andrew.
Yeah, so I just wrote 1 times bracket 6 minus 3. 1 is A11, and 6 minus 3 is the determinant of A11 minor, which is we just use the AD minus BC algorithm.
Yes, okay. That's the first summand.
Yeah, and then minus, I just put 0, since like A12 is just 0. We don't care what the determinant of A12 minor is.
Yes, let me just write it down for completeness. Okay, so this is just 0.
Yeah, then I put 1 times bracket. It's just wait. Oh, yeah. 1 times bracket 6 minus 0.
Yes. So as you can see, I'm writing everything you say, just like a step before that. But this is exactly then 2 times 3 minus 0 times 3. So let's just verify. Well, we can just do the computation. So this is 1 times 6 minus 3. 0 doesn't matter. 1 times 6, and so we get that this is in total 9. Okay, so let's just do the first step carefully again so that everyone understands why we took those minors and these coefficients. So as you can see, we start with the first entry, which is this one. This is the reason why there's a 1. And then when we strike this out, this we take this minor, the A11 minor. This is going to be A11. We're left with this. This is A11. Okay, and then we move on to the second entry of the first row. This is the 0, so this is why we put the 0 here. And then when we strike this out, we see that the minor is 2102, but it doesn't really matter because it's multiplied by 0, so it just doesn't contribute at all. But if it was non-zero, then this would be exactly how we would proceed with this summand. Okay, and then the last one is 1. So this is why this 1 is here. And then when we strike this out, we get the minor A13. This was the minor A12, and this is 2303. So this just explains how to get the first line, and this is literally I just applied the equation. I just applied this equation here above. Okay, and then from here it is just from here to the next step. It just you just remember that the determinant of A, B, C, D is equal to AD minus BC, and then you get these terms in the parentheses. Right. So Claire has noticed something that I'm going to mention right now, but that I kind of haven't been totally honest about. So there's signs, but where do these come from? So there's a sign. This is a minus. There's a plus, and there's a plus. But why are they in that way? And yes, Adrian is right. There's a rule to this, as for everything in mathematics. So any questions before we move on? Just going to make sure that we can leave this page behind. Okay, so here the yes, so the remark is that the formula that we just used is called the cofactor expansion. And the reason is that all these summands that we summed up with different signs that I'm going to touch on in a second, they're called cofactors. So so this thing that we had is the ij cofactor. So this means when we computed A11, determinant of A11, then this was a cofactor. And then we summed up, we added to this A12, determinant of the minor A12, and this was another cofactor. So we expand the determinant in terms of cofactors. These are just the summands, and this is why this method of displaying, of computing the determinant recursively is called cofactor expansion. The third point of this remark leads to the signs that Claire just asked about. There's nothing special about the first row. So you might ask, so why do we use the first row as a cofactor expansion? In fact, you can expand the determinant along any row or column. So you can fix any row or column, but just one, not multiple, and then perform this this cofactor expansion. So for example, let us maybe say we want to use this column. So this is the along the second column, then the determinant of A is also equal. It's still the same value. We'll still get 9, and you can verify this if you want. The determinant of A is equal to A12. I have to be careful. Determinant of A12, the minor A12. So we do this one. Then we have a plus A22 determinant of A22. And then we have a minus A23 determinant of A23. And you can see the only thing that's constant here is the only thing that's constant in the indices is it's the second, it's the column index. So this means is it though? No, it wasn't. Second. It's 3, 2. No, this makes sense. So this means we are in the second column. And we might wonder about the signs now. So the signs are actually exactly what Adrian suggested. It's -1 to the indices of the row and column that the cofactor is taken from. So if you take the 1, 2 cofactor, then you have to add a -1 to the 1 plus 2. If you have the 2, 2 cofactor, you have to sum -1 to the 2 plus 2. And if you have the 3, 2 cofactor, you have to sum with a -1 to the 3 plus 2. Now there's let's move this up a little bit. So if you compute this, you can see if both indices are either even or odd, then this will be a plus. Otherwise, it's a minus. That's it's an easy way to remember this. So this will be -0 determinant of 2102. This is the minor. You can just follow along and just practice minors again. Then we have a plus. The second entry is 3. That's this 3. Times the determinant of the minor, and then we strike out the middle column and the middle row. So we get the determinant of 1102. And then we have a minus again. 3 times the determinant of 1121. Okay, so just to make sure that this is actually the same, this one is just 0. This is 3 times 1 times 2 minus 0, minus 3, 1 minus 2. And unless I'm really unlucky, this should be 3 times 2 is 6, minus 3 times 1. This is 9. Okay, so just a little tip about the sign conventions again. Can I maybe shrink this a little bit? So the sign convention can also be viewed if you have a 3x3 matrix and you take a certain cofactor, then the corresponding sign is going to be alternated between plus and minuses. So if you expand along the second column, you're going to have the signs minus, plus, and minus. And this is exactly what we found here, minus, plus, and minus. If you, however, expand along the first column, the first row, which we did in the definition above, remember here we did the first row, then we have plus, minus, plus, minus, plus, minus, plus, minus, plus. Then you can see that this is exactly plus, minus, plus, which we had here. This was a plus, minus, plus. So this grid of pluses and minuses is just a way that you can double check your work if you compute determinants. Okay, so this is what I wanted to say about 3x3 matrices, and now if there are no questions, we can go to n by n matrices. And it's from this point on, it's not a big step. It's just a minor pun not intended. So what I haven't talked about really is the proof of this proposition 3.2.5, because I find it doesn't add too much to the discussion, as long as you know that this determinant is actually multilinear, alternating, and it has the value 1 on the identity matrix. Something you can just easily verify. So inside, if you have the determinant of 1, 1, 1, you can verify that with this equation, this is indeed equal to 1. And you can also say that the determinant of A is multilinear. So just as a reminder, this is we created this, and the book says that the determinant that we computed here with just I just basically gave you an ad hoc computation, but this is the function that the proposition says is multilinear, alternating, and has this property that f of in is 1, and is the only one. So make sure you keep that in mind. It's not just a random guess. It is actually the thing that that is multilinear. So this equation here that we used, and any expansion, any cofactor expansion that you can use, is in fact multilinear. Yes, the book tells exactly how it was derived, and if you're interested, you should look at it. It's just that I have to prioritize what to tell you in the short time. Okay, so then let's go into the final revision of this Yeah, it's the proof is quite involved, Jency. It's right. That's why I just can't possibly tell you all about this. So the definition for an n by n matrix is exactly, again, a cofactor expansion. So we're going to have a recursive definition. So the n by n determinant depends recursively on n minus 1 cross n minus 1 determinants. That just is clear from the from this equation, because if you give me an n by n matrix and I tell you, well, it's a sum with different coefficients of determinants of the minors, then these minors are n minus 1 by n minus 1 matrices. So just from this equation, it's clear that that this is a recursive definition. So the theorem, this is the one with the 4-page proof, tells you that, again, if you talk about determinants, we want them to have certain properties. We want to have a multilinear function. We want this to be alternating, and we want this to have the property that if we put in any identity n by n matrix, it should have the value 1. And the book says in theorem 3.2.8 that there's exactly one function that satisfies all the things on this wish list. So there's some multilinear, that's the first item. Alternating, that was the second item before, and then this property, third item. So the determinant satisfies all of them, and it's the only function that satisfies all of them. It also goes on, this second part, which is going to be useful later. It also says that if there's any other function that satisfies the first and the second item on the wish list, so it means that it's multilinear and alternating, but not necessarily the third. So the third one, we can just like forget for a second. Then this function satisfies this equation. So that if you evaluate it on a matrix, n by n matrix, then its value is a multiple of f applied to the identity matrix, and this multiple is exactly the determinant of A. Okay, so that's just the abstract way in which you can define the determinant, this theorem, but the definition is it gives you a formula which is actually can be applied. So I guess there are two things that I want you to take away from this lecture. It's first, how can you compute the determinant? And second of all, what kind of properties does it have? So remember, if you understand those two things, then I think you've learned something from this lecture, the most important bits. So in order to understand this definition better, let's have a discussion about an explicit case. And I don't want you to compute the whole determinant because that would be just too long. But just write down the first line of the cofactor expansion. So the first line. So basically, make sense of just write this down explicitly, and then we'll just say from there we know what to do. Oh, and I didn't specify. It doesn't matter which row or column you use. So you can expand along any row or column. Likewise here, I just specified the index I isn't specified. So the index I could represent any row. Yeah, it says it here. Okay, can someone tell me how I could write the first line? Just choose a random column or row, doesn't matter which one, and then just tell me what to write. Any volunteers? Yes, Adrian.
Yeah, sure. So you just start out with like the top left. So I did it for the first row. So you start out with like 1.
Okay.
And we know like the sign is also going to be positive for this one because it's the first one.
Yes. So let me just write down the signs. So you could either do it this way. You only need the first row. And we could also yeah, just go ahead. What do you want to say?
Yeah, and then you just multiply it by the determinant of like basically the lower right hand like matrix, which is 3 by 3. And then basically just continue. So it's going to be +3 because it's going to be -3 times -1.
Right. Now we have taken into account this sign. So this is the minus sign that we have first. And then we also have the coefficient, the entry at the 1, 2 position, which is this one. This is why there's a minus 3. And then, yes, go on.
Yeah, and then you just get the determinant of, so in rows 8, 2, minus 2, 3, 5, 3, 0, minus 2, and 4.
Yes. And this is just by, this we just obtain by forgetting this and this. So this is exactly the matrix that's left over when we strike these out. And let me just pause for questions. Is everyone following this? Is someone wondering what the heck is going on? No, at least if there are, then they're not telling us. Okay, so please keep going.
Yeah, and the next one, it's just going to be +1 because the sign is positive, and we have 1 as an entry. And then it'll be the determinant of 8, minus 4, minus 2, 3, minus 7, and 3, and 0, 3, 4.
8, should not put them too close together. 8 minus 4 minus 2, 3 minus 7, 3, and 0, 3, 4. Yes, that's correct.
Yeah, and then for the last line, it'll just be -4 times the determinant.
Oh, I just realized I just made this matrix too big. Yes. Sorry,
yeah.
Continue.
So the last one was just like 4 times -1, so we'll get a factor of -4. And then we just multiply by the determinant of basically like the lower left 3x3 matrix.
Yeah, so we strike this out. So we're looking now at this position in the first row, and so we strike out this, and then we just read of this minor, the matrix remaining: 8 minus 4 2, 3 minus 7 5, 0 3 minus 2. Yep, that's correct. And the signs, so it just highlighted these signs here. There's a plus in front of the first one, the minus, the plus, and the minus. And you could have also gotten these that we just maybe in a different color. Let me just say, well, we could have also gotten these as -1 to the 1 plus 1, -1 to the 1 plus 2, -1 to the 1 plus 3, and we could have gotten this one as -1 to the 1 plus 4. This was just choosing the first row. We could have chosen any other row. And if you want to actually compute this, and I can only encourage you to do it, then you'd have to now do this cofactor expansion for every 3x3 matrix in this equation and in this term, which I do not want to do right now. But for practice purposes, this is excellent. Any questions? Thank you, Adrian. Okay, so before we take the break, I think there's, let me just check. There is, I'm confused. There's one more page I wanted to show you. So first of all, if you want to have more exercises in computing determinants explicitly, there's an exercise in the book. It's called example 3.2.9, and it walks you through the step of each step of computing a 4x4 determinant. And they actually go all the way to the end. But their matrix is simpler than the one I chose here. And then, so recall that this theorem is very interesting. And I guess this is like one of those lucky coincidences in math that we actually have this theorem that, remember that the determinant of a 2x2 matrix, yesterday when we were starting out with this, what was the motivation for a 2x2 matrix to have the determinant AD minus BC? So recall the determinant of ABCD as AD minus BC was motivated by the fact ABCD is invertible if and only if the determinant of A, B, C, D, and this is terribly small, determinant of A, B, C, D is non-zero. So that was the whole thing that we started out with yesterday. Yes, exactly. Yuan wrote this just in the chat. And now it turns out that after we've gone to n by n matrices, this fact is still true. So that's just, I think this is really cool because it gives us a tool. I think that this justifies why the determinant is very useful. And computing the determinant is just a straightforward computation. So you can plug this into a computer, give it a matrix, and tell me the answer. And then if this matrix was a matrix that you found from a transformation, say, you could actually say, well, now I know whether this transformation is invertible or not. And if you just look at transformation, say a rotation, a projection onto a subspace, whatever, it's not clear per se if it is invertible or not. The determinant, however, is a very brute force method, and a very it's highly non-trivial that something like determinant exists, that there's a tool out there that gives you all these, that gives you this assertion, and that tells you so much about a matrix. So the theorem that I'm talking about is this 3214, and it says that an n by n matrix A is invertible if and only if its determinant is non-zero. That's the statement. And we saw explicitly that this is true for 2 by 2 matrices, but it's true for any size matrices. So yeah, the remark I kind of took away that this perfectly agrees with the discussion that we had at the beginning. And I can only remind you, I think we talked about this. So if you have, if you think about this 2 by 2 matrix A, B, C, D as a transformation, then it sends the vector 1, 0. So this is just a transformation. It sends the vector 1, 0 exactly to the first column, because if you multiply A, B, C, D with this identity, the first standard basis vector, you get the first column. And it sends the second one to the second column, B, D. Then you can kind of think about this graphically as sending the standard basis, which is 0, 1, 1, 0 in R2. This is sent to some other vectors, sent to BD and AC. And this is invertible if and only if they're non-parallel. So if the image, there's some parallelogram associated to this. So this is invertible if the image is all of R2, and this is equivalent with saying that BD is not parallel to AC. These are the two image vectors of the basis elements. And then from there, you can like go all like the thing that we talked yesterday about the fact that, well, now there's the area here is the determinant of A, B, C, D. And this area is exactly 0 if the parallelogram is collapsed into like a degenerate parallelogram. So this is a very beautiful idea. And just to give you like an outlook, we're not going to cover this, but of course, if you have a 3 by 3 matrix, then you can think about the vector A1 as the first column, and the second column we can call A2, and then the third A3. Well, you can think about this as 3 vectors now 3, and you can see there's a volume associated to this, and this is called a parallel epipad. I hope I pronounce this correctly. You never know. So this is the volume of this thing for the vectors A1, A2, A3 is equal to the determinant of A. So this has higher dimensional versions, what I just told you about this. Right, so that's just some intuition about this theorem, which we're not going to prove because the proof is too long. Any questions? Okay, so there's 2 more pages about determinants that I want to go through. Let's take a break first. And let's come back at 10 past 2. And then we'll continue. Resume the recording. And we left off 10 minutes ago with this theorem that a matrix is invertible if and only if its determinant is non-zero. This has a lot of implications. For example, we showed before that a determinant is invertible if it has full rank. So now we could talk about what it means. Why is determinant? So this is maybe just a note. I shouldn't get sidetracked, but so just an observation. This is something interesting that if the rank of A is less than n for n and for A and n cross n matrix, then A is not invertible. This would imply that the determinant of A would have to be 0. So this combines the previous theorem, but also something that we've done last week. So the question that I actually don't really have time to answer is why is that? So could you go directly from here, skip invertibility, and go directly to this? And you can actually argue that, so a partial answer to this question, which I'll not make precise, is that the determinant of A is non-zero if and only if the determinant of the row reduced echelon form of A is non-zero. And of course, if you have, and then from this answer, and this is something we have to prove, and this is not too hard to prove if you have the right idea about this, then, so of course, imagine that R, let's call R the RREF of A, has a rank less than n. It has a row of zeros. And this implies that the determinant of something with zeros. So if there's a row of zeros here, then this is not very nicely written. So the determinant of something where there's zeros and then anything else. So this star just means just put in anything you want is 0. So this is just observation that we can make with the rank, invertibility, and the determinant. Maybe you can actually prove this. Maybe you can actually prove this with the properties 1, 2, and 3 that we opposed. Okay, so let's move on to further properties. There's 2 more pages I want to talk about. The first property is very interesting because so matrices can be composed by multiplication. And if you happen to have a product of matrices, then you have to compute the determinant. You may wonder, what is their determinant? So this proposition says 2 things. And the first one is that the determinant of a product of matrices is equal to the product of the determinants of the matrices. So you can compute the determinants separately and then multiply them together. That's very nice. And it also says that if the determinant is invertible, then the inverse matrix A inverse has determinant 1 over the determinant of A. And the good thing here is that the determinant of A is actually non-zero if A is invertible, which we have to assume here in order for this expression to even make sense. Okay, let's prove these two things. The first one is the more difficult one. The second one does not. Will follow from the first one. So if we define a function, and this is f. This goes from f of b, and we just say that determinant f of b is the determinant of a times b for a fixed matrix A of size n by n. Then we can observe that this is multilinear. And alternating, because if you think about the matrix product A times B, so how do we observe that this has 2 of the properties that we want for determinant? If we write B in terms of its columns, so this is B1, B2, and so on, Bn as columns, then AB has columns which are given by A multiplied to B1 is the first column of AB. AB2 is the second column of AB, and so on. You can just check that the way we define matrix multiplication actually gives us back this property, because if you multiply 2 matrices, then the first column is just the first column of the resulting matrix will just be this column paired with all these rows. And so you can verify and convince yourself that the columns of AB of the product will actually depend in this way on the columns of B and the matrix A. But now observe that that if we have a matrix, so we have, say, B1 plus Z, B2, let's call this matrix B prime, B2, B3, and so on. So if we have 2 columns, we add 2 different vectors for the first column, then this means that AB has first column A, B1 plus Z, and all the other columns are unchanged. But this last column this first column is precisely the column, is exactly the sum of the vectors A, B1 and AZ. So this is the first column. So when we apply now the determinant to, sorry, not the determinant, if you apply the function to this matrix where we have B1 plus Z as the first column, we want to show that it is linear in this so that we can pull the sum apart and have F of B1 and the other B's and F of Z and the other B's. That's what we're trying to show here. So it's this is the first column. Then we have the other columns unchanged. But by definition, this is equal to the determinant. And now we can okay, let me just A times A times this matrix of B1 plus Z, B2, Bn. And now we use this property above this. Let me just make a box around this. So this box, we basically just computed the matrix product of A with B, where we have a sum of vectors in the first column. So this next equality here, this is due to the box. This is what we use here. We should not draw within function. So this equality is due to that observation. Now we have the determinant of AB1 plus AZ1 plus AZ as the first column. So this is a matrix with the first column being a sum of two vectors. And then we have the usual the columns unchanged after that. Bn. And so now we use that the determinant is multilinear. And now I kind of want to shrink these things. So now that we've converted this problem of showing that F is multilinear in using that determinant is multilinear, we can just detach this as the determinant. So just think about everything in these square brackets as one matrix. It doesn't matter that they come from A and B. So then this is the determinant of AB1, AB2, ABN. And we have the second term, which is the same remaining terms, but the AZ column. So we have determinant of AZ, AB2, ABN. But this is nothing else but F applied to B1, B2, Bn. So basically, this is the matrix B with columns B1 to Bn. And the second one is just the function applied kind of, where do I put this thing? The second one is just Z, B1, B2, Bn. So we can show that if the function f defined in this manner, that was the definition of f for a fixed A, is multilinear. And similarly, we can also show, and this also works for other columns. Then the first one was just rotational ease, so otherwise it would have been even messier. So this means that f is multilinear. Similarly, f is alternating. But then these two things imply by theorem 4.2.8 that f of b is equal to the determinant of b times f of I. Just remember, let me just go back to that. Here, this is what I'm using. This is exactly what I'm using. So if I have this function which has two of the properties, not the third one, but only the first two, which I just showed you, I defined the function should be on a matrix, the determinant of the matrix multiplied by another matrix, but that second matrix is fixed. So I'm writing this identity in terms of the defined function f of b. So I have a function, and this is equal to the determinant of the matrix times f evaluated at in. So let me write this down. This is what I wrote here. But then the question is, what is f of I? Well, this was by definition just the determinant of a times I. I is just a special case for b, and this is the determinant of a. So we can simplify this expression and write that this is the determinant of b times the determinant of a. So we have, and of course the left-hand side was determinant of a, b. Because I have these two properties, I can invoke the theorem 4.2.8. So we've shown the first thing. This was the more involved part of the proof. Are there any questions?
Just on the last line where you have equal to f of b1, b2, should the second term, does it actually start at b1 or does it start at b2? Like the f of z and then
oh yes, again? Thank you.
Okay.
This is true. Thanks for telling me. Okay, so this was the heavy lifting. Now the second part will look like a breeze compared to this. So the second part, if we have A inverse and we assume it exists, then A inverse times A is equal to I. That's the property. That's the definition of in the inverse of a matrix. Now, if we apply determinant to this, then we know that, I should have written the other way around. We know that the determinant of A inverse A is the determinant of the identity matrix, and this is by assumption that what the third item on the wish list is 1. But now we use the first statement of this proof that we just proved on the left-hand side. This is equal to the determinant of A inverse times the determinant of A. And now if you divide by the determinant of A on both sides, which we can do because the determinant of A is non-zero, because A is invertible. That was the proof, the theorem that we didn't prove on the previous page. Gets us the result that the determinant of A is 1 over the term. Oh, sorry. Yeah, divide by the determinant of A. So I want to write the determinant of A inverse is equal to 1 over the determinant of A. And that's all we need to do for the second step. The first one is the one with heavy work. This is a warning. The book does this too, but the book uses rows. So the proof of this proposition in the book will be slightly different. They literally just use the opposite order of multiplication, A and B. But the argument is the same. So to finish the discussion about determinants, are there any questions? Let me wait for questions. So this property of having actually both of these properties are very useful for transformations, because so the matrix representing a transformation depends on the chosen basis. That's what we learned. But we also learned that when we change the basis, the matrix changes by conjugation. So this means if A was the original matrix that we got by choosing one basis, and then we choose another basis, we just multiply with P inverse P. So the corollary of this proposition that we just proved is that for linear transformation, the choice of basis doesn't matter. So the determinant of the matrix presenting a transformation in every basis, it's the same. And that's really cool, because now we can say, we can basically say, what's the determinant of the transformation? And you might ask, well, which basis should I choose? And then you just answer, well, it doesn't matter. They're all the same. Oh, I forgot a closing bracket here. So it says, no matter which basis we choose on V, the matrix presenting a transformation has always the same determinant. Let us quickly look into the proof. So we know that for a change of basis, we know that T alpha alpha is equal to I alpha beta T beta beta I alpha beta inverse. So now if we take the determinant of this, also this means that I alpha beta is invertible. If you take the determinant of T alpha alpha, then this is the determinant of these three matrices together. Beta T beta beta I alpha beta inverse. Now we use the first property of the theorem that we just proved. So this is the determinant of all these matrices separately. So we can just have I alpha beta. Then we can have the determinant of T beta beta, and then we have the determinant of I alpha beta inverse. And now we use the second step, the second property of this theorem. It says that, well, this is the determinant of I alpha beta. Also notice that when we take determinants, this will be a scalar. So the order doesn't matter. We can commute those elements. And then we have the determinant of 1 over alpha beta, because we just apply the inverse, that the inverse has the determinant that is inverse to the other determinant. It's a lot of writing and a lot of indices. But at the end of the day, the important thing is that these two things cancel out because they are just inverses of each other. So we get the determinant of t beta beta, which is what we wanted to show. So no matter which basis we are in, if you change the basis, then the determinant doesn't change. So Yuan's question was, no, so you might have two different matrices with the same determinant. It doesn't mean that they have to represent the same transformation. Basically, all non-invertible transformations have determinant 0. It doesn't mean that all non-invertible matrices it doesn't mean that all non-invertible transformations are necessarily the same. Yes, so you can, depending on whether you have alpha and beta switched, beta and alpha, you could put the inverse here or here, and then it would just carry through. Maybe this was the thing that the book did. So then we would just carry the transformation through, and then we would still have the same end result. Oh, actually, no, I don't need to change all the. It's as long as you're consistent, it works out.
Sorry, in line 1, should it be t beta beta equals identity alpha beta? And then t alpha,
no, I
alpha.
think this convention is fine, because if you go from v to v, if this is t, and you have the basis alpha, so if this is the basis beta, and then you compose this with alpha, then this will be the identity transformation. And here you have Rn, and so this will be t beta beta. And on the left, you're going to have the identity transformation from alpha to beta. So this is what you want to compose: I alpha beta, t beta beta. So this is exactly. Sorry. Yeah, this is actually then the first. Yeah, sorry, you're right. So what I could do is, I believe, just do this. Then it should be correct. Yes, you caught me. I did mix up some indices here or there. Maybe, hopefully this fixes it. But I think the argument of the proof does not depend on these indices. You can figure it out and then practice this. So I think this is not correct, but I'd rather move on because there's some important things I need to tell you. Any other questions? Okay, so before we get to eigenvalues, now that we know that the choice of basis doesn't matter for the determinant of the transformation, it is natural to just say, well, the determinant of a transformation is just a determinant of its matrix in whatever basis you want, and the choice doesn't matter. So that's the important part. Any choice of basis is fine. And then after that, there's just a statement that says, well, the transformation is invertible if its matrix is invertible. And so this is yes. So once you connect transformations with matrices, and you know that the determinant of t, so I could say that t is invertible if and only if t alpha alpha is invertible. And then this is equivalent with determinant of t, which is determinant of t alpha alpha is non-zero. There might be a more, I could say more about this proof, but since we talked so much about the determinant of transformation, sorry, of the connection between transformations and matrices, I think this proof does not require much more justification. I think the book has a better has something to say about this. So if you're not just satisfied with what I just wrote here, then please look at the book. That's the position of the number. Okay, and lastly, also something that I don't want to go into detail. Well, this proposition looks exactly like the proposition we just looked at for matrices. So it says that if you compose two transformations, then the determinant behaves in a certain way. So this proof, you can just trace this back to the property. Which one was that? It was 337. So we just looked into this in very detail. So then we can just trace this back to 337 about the matrices this should not be S, one of them should be T. So this is just a matter of bookkeeping and going back and forth. All right. Any questions about determinants before we go to eigenvalues? I am rushing a little bit today, and yesterday I was rushing too. It's because we're still behind the schedule, and I'm trying to tell you the essentials that you need to know, and then leave out some things, or just go through them quickly, so that we can catch up. But this means so because I'm trying to catch up to the other sections. This means there's even more responsibility on you to actually stop me when you want me to go into more detail. So it's and don't be ashamed of asking or stopping me. And I'm happy to slow down whenever there's a question. I'm happy to go through details in my office hours. I would not like to record them because students, it discourages some students to ask questions if they know they're recorded. So for that reason, I don't want to record office hours. But if you can come to my office hours, then just we can go through all of this again in detail. Okay, so eigenvalues. This is now section 4.1. And this is the first part only. Next week, we're gonna look at eigenvalues much more. I think eigenvalues is the first section really, where you will be able to appreciate everything that we've learned so far in this course. So now you can realize how powerful the tools that we've acquired over the past weeks are. And so I think this is if you start this section with this point of view, I think you can actually enjoy all the power that you've acquired. So we've worked out quite hard, and now we can flex our muscles. Okay, so first an observation to motivate this discussion. So if you have any transformation, just for argument's sake, let's look at R2 because this is easy to draw. Actually, let me just make this bigger. So if there's transformation from R2 to R2, let's call this T, then T can really do anything to a vector. It can, so this is V. T of B can be just as wild as you want. It can be stretched, it can be rotated, it can be flipped around like backwards. There's no limit to what transformation can do. So they're very badly behaved and very uncontrolled. What would be nice though is if we had a vector W that is not rotated. So the direction is the same, only the magnitude changes. So this would be now TFW. And those kind of vectors it's not guaranteed that those vectors exist, and it's not trivial how to find them. But the first definition of an eigenvector is precisely concerning those kind of vectors. And because zero is always just sent to zero, this is a boring example. So we want to exclude the zero. That's just true for every transformation, as we've shown many weeks ago. So let's ignore this example. So the eigenvector, or an eigenvector, is a non-zero vector that is only stretched. And how do we write this down mathematically? Well, it means that the image of the vector v under the transformation is just a multiple, meaning that T of v has to be lambda times v, where lambda is just a scalar. So this is just scalar multiplication. If you look at v, then maybe 3 times v would be this. And if T happens to send this vector to this vector, then it would be true that T applied to v is the same as v multiplied by lambda, maybe 3, maybe 2, maybe -1. It could also be negative scalar. So I wrote here in blue that this means v is only stretched and not rotated. But notice it's very important to have this definition, like be aware that it has to be non-zero. So this is crucial for the definition. Okay, and then the second notational definition is, what do we call the scalar? So if there is a non-zero vector v such that it's only stretched under this transformation, then the lambda is called the eigenvalue of this vector. So we can say that if this equation is true for any vector and any scalar, so they kind of have to find each other. It's like a pair of a vector and scalar. Then one says that v is an eigenvector of T, and with eigenvalue lambda. You can also say that lambda is an eigenvalue of T with eigenvalue with an eigenvalue v. That's just notation. Are there any questions about this definition? So I wanted to look at examples now to give you an intuitive idea about whether you might have seen this before. And last week we spent a lot of time looking at the projection onto the line of slope m. So remember that what this was. This meant we looked at R2, and then we had a line in there. It doesn't really matter what slope it is. I'm not going to do any computation right now. But then let's say that there's a vector v, and you want to project this onto this line. So you take this, you compute the projection. There's a formula that the projection onto the line with vector d. So this is the direction vector d of a vector v is given by is a dot product v times d over d times d times d. But the important bit is just by graphically looking at this is much more helpful now than any formula. The projection of v onto this line will be this vector. Now the question is, just graphically, can you tell me, and this is actually the same question I've asked before, just in a different context. Can you find vectors which are not rotated? Because obviously the vector here is a little bit shorter than the original vector v, and it's also rotated to the right. So it's just completely manipulated. Are there vectors that are only stretched and not rotated? if someone, yes, someone did every vector along D, any vector on the line, vectors along the line, and perpendicular. Yes. So the answer is like all of the answers are correct. They just answer different ways. So let me draw them in maybe one in red. So any vector. So this is, if this is now say W, then the projection of W onto D is still W, because once you're on the line, if you project onto it, it doesn't change the vector. But you could also write this as 1 times W. And now we see that this is precisely an eigenvalue equation. So this is an equation of the form TV is lambda V for lambda equals to 1. So this is an instance. You have to be able to pattern match the abstract eigenvalue formula, the eigenvector formula, with concrete instances. So in this case, T is the projection operation, and then W is the vector that we apply this to. And when we apply this, we get it stretched. Well, actually, it's not even stretched. It's just multiplied by 1, which is also a stretch. Let me just close the blinds. The sun is blinding me. All right. So another vector, and that's something Jancy just wrote in the chat, was if we look at a vector perpendicular to this, what happens in, let's call this U, what happens if we project U onto this line with direction vector D? It's just going to be 0 because it's completely perpendicular. So it means if we squish it down, it's going to be 0. So this is 0. But a somewhat different way of writing this is that this is 0 times the vector U. So we've pattern matched another equation to fit the format of the eigenvector equation. So this means the projection has 2 different eigenvalues. Now the question is, are those the only eigenvectors I drew, or are there more eigenvectors? So if you take like half of U, it's a different vector. It's still an eigenvector with eigenvalue 0 because it's also squished to 0. If you take like a longer vector along the line, any vector along the line will be an eigenvector with eigenvalue 1. Okay, so I think that's all I would say about this example. Any questions sparked by this example? Let's have a look at a more computational example. So let's look at a matrix, and this is actually in the book, the first example that they give. So whatever we don't cover in this example right now, you can just look at it in the book. So just by defining a transformation by matrix multiplication, we can observe if we multiply this matrix with 1, 1, what we see is 2 times 1 was 1 times 1. And in the lower entry, we get 1 times 1 plus 2 times 1. This is equal to 3, 3, or differently written as 3 times 1, 1. So voila, we have another format. So like this equation, this is of the format T sub A applied to some vector. We could call this X. It's equal to 3 times X, or let's call this lambda 1. This is a pair of an eigenvalue and eigenvector. And we've shown that it satisfies this equation, saying that it's only stretched. It's not rotated at all by this transformation. Likewise, if we multiply 2, 1 and 1, 2 with the different vector 1, minus 1, then we get 2 times 1 plus 1 times minus 1, 1 times 1 plus 2 times minus 1 is equal to 1 minus 1, which is just exactly 1 times 1 minus 1. If we remove this lambda 1, if we just have lambda, then of course this is exactly the same format again. So there are two different, there's two vectors, 1, 1 and 1 minus 1, which are eigenvectors. But just to show you that this was actually, I had to like choose these carefully. I can also compute just any arbitrary other vector. Like let's say we multiply 2, 1, 1, 2 with just the vector 1, 0. It's going to be 1, 0. This is going to be 2, 1, the first column. And this is not equal to lambda times 1, 0 for any lambda in R. So there's no way that 2, 1, 2, 1, which is pointing to like this direction somehow, and 1, 0 in R2, there's no way that you can scale one of them and get the other one. There's just no way. So these vectors that I presented you to you above, they're actually special. They have they're different than the most of other vectors. Any questions? Lambda can be 0, as we've seen in the first example. So here, just to be clear, so U is an eigenvector of the projection onto D with eigenvalue 0. The eigenvalue can be 0. The eigenvector cannot be 0. That's the important bit. Maybe we should. So yes. So let me make this clear here. So this is non-zero. This is the eigenvector, but the eigenvalue might be 0. There's no restriction on the eigenvalue. Yeah, but it's good that you asked. It's important to clarify, and I bet someone else in the class also had the same question. So I kind of want to go on because like the story is like so natural to tell that I just don't want to stop. Maybe let me make one more remark and then I'll stop because we still have 2 minutes remaining. So the question is that should come up in your minds now. I told you just about these special vectors for a given transformation. How do we find them? Is it like a way? Is it like a recipe to cook them up? Well, it turns out there is, and there's just an observation that we can make. Well, what does it mean? When is T of V equal to lambda times V true? For some lambda and V non-zero. So I don't even care what they are. As long as you give me some pair of lambda and V, which satisfies this equation, I'm happy. So let's manipulate this equation a little bit. So this is equivalent with saying that if we subtract lambda V from both sides, we get that 0 has to be equal to T of V minus lambda times v. But this is now T of v minus lambda times the identity transformation on v of v. And then finally, we can write this as a new transformation, T minus lambda times the identity transformation applied to v. So it's very important to understand that this is a new linear transformation. So what does this now tell us? This new transformation that I just created depends on the original one that was fixed and the value lambda. But now this equation just tells us that v is in the kernel because it's mapped to 0 by this new equation, T minus lambda identity v. So we can make a transformation out of T and this lambda so that all the eigenvectors or like eigenvectors with eigenvalue lambda will be in some kernel. And so the proposition that basically is proven just by answering this question, these 3 lines, it says that a non-zero vector v is an eigenvector of T with eigenvalue lambda if and only if it is in this kernel of this transformation that we created. And then, of course, every answer gives us a new question. But I promise I'll stop now and I'll not continue. This is something that we're going to continue next week with. So fine, we know now for like what the v has to be, but obviously not every number works here. Like which numbers can this be anything? And the answer will be no. So we're going to continue asking for which lambda are there eigenvectors. Okay, so I want to stop here, but let me also remind you one last time about this this hiccup between columns and rows. So I want to, because I don't want you to be confused about this. There's going to be one question on the assignment coming up about determinants, and the assignment is made for every section. So I don't know if it was wise or not wise to talk about columns instead of rows in my section, but I like this way more because it's more intuitive to think about these as vectors, and it's more intuitive to think about them as multilinear functions, and it's also nicer to write. So remember that when we write that the determinant is multilinear, then we can both say in rows, in columns of A, but we could also have said this in terms of in rows of A. So the column perspective is the one that we chose. The determinant of A, well, A is made up out of columns A1, A2, AN. Then the determinant of A can be thought of as a function depending on A1, A2, A3, and so on. But we could also have chosen the row perspective, and then we would have said, well, let us think about A in terms of its rows. You can already tell like this notation is not as nice. And then the determinant can be thought of as a function depending on the first row, the second row, and the last row. And the statement is just whatever we had about the determinant sort of columns, multilinear, alternating, and so on, is also true for the rows. So it's alternating and multilinear. Okay, this is well stopped. Let me stop the recording.